Hello and welcome back. We now want to talk about how we can find the root of the function, or where does the function cross the x-axis. And we want to use this as an example how we can exploit the functionality of deep learning frameworks for numerical analysis. So what is root finding about? In many cases we want to find the position where the function crosses the x-axis or takes a particular value in general. So for example, f of x is a simple value y or equals a function. And we can rewrite this as the root of the function. So where does it cross the zero line? So for the first example, where does f of x minus y cross the zero line, or the function where is it identical and crosses is always zero, or at least in a specific point. So we can see this here on the example on the right. This is a simple function, essentially a wavy slope down, and we can see here that from the known solution of x equals 0.755 that there this function crosses the x-axis, and we now want to find this spot numerically. There are many root finding algorithms, some are more efficient than others. So for example, we could of course step through all the values, but please don't do this, this is very inefficient. So there are bracketing methods, right? So we want to determine a smaller and smaller interval that contain the root, so the point where it crosses the x-axis, and then we stop when we've reached a given accuracy or are at a given tolerance. One method is called bisection, so we start with an interval AB and evaluate fn(a) and fn(b) at these borders of the interval and see if they have the opposite sign. If yes, then we take the middle of the interval again and so on, and modify our interval so we make this interval closer and closer by always going into the middle of the interval and see if the root of the function, i.e. if the function has the opposite sign on either end of the smaller and smaller interval, is contained on those interval borders. An extension is the regular falsi. It's similar to bisection, but we use the x-intercept of the function at the endpoints instead of the middle, so it's a bit more flexible, that we don't have a fixed middle point, but we sort of vary this on the function behavior. This makes it a bit more efficient. Then there are a number of iterative methods. For example, Newton's method is very efficient if we can compute the derivative of a function. So the idea is that we assume that the function has a continuous derivative, or at least it has a derivative at the points that we need to evaluate these. We choose some initial point x0 and then iterate the following equation. We'll come to that in a second. This is very efficient if we have a suitable starting point. If we choose a not so suitable starting point, the algorithm may not converge. We can also use the second method, is essentially replacing the derivative with finite differences, removes the requirement for the derivative, but it also then means it's not quite as efficient as Newton's algorithm. And the fixed point iterations, of course, many more, or combinations of those that can be used. We'll stick with Newton's method here, and the general idea is that we start from a suitable starting point, x0. This is our initial guess, and it has to be good enough that it's not extremely close to the root of the function, but it's also not very far away. Now we calculate the value of the function f of xn, where we take x0 as a starting point. We do this repeatedly, so we already take xn instead of just x0. So we calculate the value of the function at this point and the derivative at this point, starting with x0, and then we can form the tangent given by the equation for y here, and we want to find the root, so we set the tangent to 0. Now after some massaging of the terms, we can come back to this iterative equation that we have seen in the previous slide. So we iterate on xn is the previous one minus essentially the value by the gradient. So how do we do this in deep learning frameworks? We take the example of PyTorch here. One of the most underrated features of deep learning frameworks is that we can use it to calculate large matrix operations efficiently on GPUs, but also because we need in the backpropagation the derivatives. And since everything of the numerical optimization and moving it to GPUs and so is already inbuilt, we don't have to do the heavy lifting ourselves. So we still choose a starting point x0. So in PyTorch language, that means that we have to create a torch tensor, and here we put in our initial guess. This is a numerical value, and the key point is that we tell PyTorch that we require grad equal true because we need the gradient later. So this is telling PyTorch keep track of the derivatives. And now we iterate, and this is Newton's function there, and now so we repeat until convergence, we evaluate the function, as we said. We also then compute the derivative and the gradient, and then we update x new or xn plus 1 with the ratio of the old one minus y and x grad, where x grad is the gradient. We also introduce a learning rate for optimization for the convergence. Of course, that's not strictly necessary, but it depends then on the numerical stability given the function that we have. And then we update the function. X is now x new, right? So this is the x1, so the iterative part, where we save the value that we've just computed. And in order to put that there, we also need to make a deep copy in PyTorch. So we need to clone it and detach it from the previous computational graph in PyTorch so that we really have a new variable. And remember, the key point is that we have required grad equals true, so we need to put that there. So essentially, this last line is the update step, and we also need to put in all the little magic from PyTorch to tell us this, like, this is a new variable. It's no longer associated with the previous computation graph, so you can start again with a new value. You require the gradient tracking and iterate on those. So this, depending on the function, works, but may or may not be inefficient, right? Because we iterate the derivatives and the gradients ourselves. So in many cases it may be better, but you have to try for your use case to use the loss function, the optimizer, as we use for normal deep learning. So there we again have our torch tensor. Now we put the optimizer there, 0 grad, as we did before. We have the value of the function, and now we find a suitable loss function that is useful for our problem, and then use the optimizer to find the next step. As I said, depending on the problem, the previous direct implementation of Newton's method may be just as efficient, or maybe even a bit more efficient, because you do this directly then, rather than having the full optimizer and loss function approach, but it really depends on the problem at hand.